then the available energies is going to increase square root of energies, so something like this. This is available energies. And we just cut it here, we call the Fermi energies. Fermi energy. Because this Fermi energy is the most energetic electrons. Fermi energy is the energy that the free electron can have. The maximum, no, I have to write down correctly. The maximum energy that free electron can have. And that is going to be the Fermi energies. That is going to be called in the Fermi energies. So the maximum energy is Fermi energies like this, then available energy states. This is not the energies of free electrons in a metal or in a solid of free electrons. This is the available energy states. It's nothing but energy states available for the electrons to occupy. And actually, what kind of energies the electron can really occupy is depending on the temperatures, the external energies. It just depending on that, depending on the energies, electric fields or whatsoever, the external energies, the free electron can have these available energy states. Among these available energy states, electron may have different energies according to the probability for the electrons to occupy that energy states. Okay? At this point, let me just give you the K-space. This is, so far we have discussed mainly with the N-space, okay? N-space means the Cartesian coordinate nx, ny, ng, and then we are going to talk about the 1/8 of this volume of a sphere, okay? That is the N space. Now, in the K space, we can regard as in the K space in that the K is going to be related with 4 pi over n, something like this, right? So Kj, let's see, Nj, something like this. Okay? And J is equal to X, Y, and Z things. So, in a K space, the orbit state 2 pi n j over L corresponding to one orbit state. So 2 pi over L is contains 2 pi over L is the unit of one orbital state, which means the number of states per unit volume in K space is going to be 2 pi over L minus 3. That is going to be the number of volumes, number of energy states, and that is 8 pi square, and then the number of states per volume. This is corresponding to the volume. So per volume is going to be 1 over 8 pi cube, something like this, right? And sometimes it's easy for us to discuss the energy states in terms of the K rather than in n space. So that's why I'm writing this. So the density is going to be in a K space. This is nothing but the L square, IQ, 4 pi over 3 KF 3, and then this KF is the radius of the sphere, and in this KF is going to be Fermi surface wave number, something like that, okay? And then that is going to be 3 pi square n 1 q. And the energies at the Fermi surface is going to be 2m kf square, and then that is going to be 2m 3 pi square n v 2/3. And then we call this Fermi energies. Now, on Wednesday, we're going to discuss about the energy states. What is the really the electron energies, free electron energies in a solid? In order to find that, so far we have seen that the available energies and that density, state density, is such and such. Now, if we know that at certain specific temperature, if we come to know that the electron have such and such probability to really occupy that energy states, then the energy of the electron is that energy. So next time what we are going to do is we want to see what is the probability of electrons to occupy that specific energy state at certain temperatures, things like that, okay? Okay, I'll see you on Wednesday. Do you think we can have a class on the Wednesday? Because there's some construction going on the third floor, and I don't know